Okie dokie, welcome back. So we're going to be moving on to the next stop point now, which is apply the modeling of projectile motion to quantitatively derive the relationships between the following variables: initial velocity, launch angle, maximum height, time of flight, final velocity, launch height, and horizontal range of the projectile. So let's get started on that. Let's firstly just look at some of these terms that they've used in the dot point, and then we'll look at a specific scenario in order to try to derive these relationships. So what we're doing is applying the modeling of projectile motion. So what does that mean? As we stated in the previous dot point, we've now developed a model for projectile motion in the sense that we have a picture in our mind where we only consider gravity as the only force that acts on a projectile, and we assume that we have zero air resistance as well. This simplifies things a bit because we only have acceleration acting in the downwards direction, and that leaves our horizontal direction nice and free and without influence from anything else. So in the scenario we're going to be looking at here, let's say a blue block, and we have our ball, which we're going to be launching in a sort of top right direction. It's going to go up, reach maximum height, and then come back down to the ground. So basically what we've looked at before is that this will draw out a parabolic shape as it goes up and comes back down to reach the ground. So this is the model that we're going to be using for projectile motion. When we have our initial velocity, so let's draw that in now. We have our initial velocity u. We've shot it up into the sky, and we can break this up into two independent components. We have our up-down component, which we're going to call the y direction, and a sideways or sort of left-right direction, which we're going to label x. So basically what we've done here is we've taken this vector, which we've labeled u, which is going to be our initial velocity, and we've broken it up into uy and ux. As we recall from previously, the reason being that gravity is only acting in the downwards direction, leaving ux to be completely independent. I mean, ux is going to be constant all the way through, right? It's only uy that's going to change as the projectile goes through the flight. Now, what we can also do is, with respect to this horizontal direction, is define an angle called theta. This is going to be our launch angle, and it's going to be basically saying, when you threw up your projectile, what was the angle between the initial velocity vector and the sort of left-right plane that you've launched it at. This is going to be important because it allows us to very easily break these down. This is what we did previously as well. Now, so we've got initial velocity, we've got launch angle, initial velocity that can be broken down. Maximum height, what's the maximum height? Well, that's just going to be the height between the point at which the projectile reaches its maximum height with respect to the ground. So if we just go from there all the way down, that's going to be our maximum height. So let's just call this HM. So H for height and M for the maximum. Time of flight, how long does it take for that projectile to go from the beginning all the way to the end? We're going to call that TF. So that's going to be our time of flight. Final velocity, well, what's the velocity it reaches at the end? Now, all the way at the end is going to be 0 because it's no longer moving, but along the path there's going to be some interesting points where if this is our beginning point and this is our end point, for example, if we're just looking at that first bit of the motion, at this point the vertical velocity is also going to be 0, right? But we'll go through that when we start deriving some of these. The launch height, so as we were saying before, because this is launched from some height above the ground, we're going to give that a definition as well. So in this case, that's going to be HL. And then the horizontal range of the projectile. That's just going to be the distance from where the projectile started all the way to the end. Because this is only horizontal, we're sort of ignoring that vertical component, and we're saying how far away does that projectile reach, right? And we're going to call this capital R for range. Okay, so we've got all our definitions now. And because we want to quantitatively derive the relationships, quantitative meaning that values and numbers are going to be involved, this is going to be not only a sort of pictorial representation of projectile motion, our model is also going to have to include mathematical equations too. So this is where the rectilinear equations of motion that you've covered in year 11, this is where they're going to be coming in. And those equations can be seen here in the top right corner as a reference so that we can basically start deriving things. What we've done here as well is taken that crude drawing from the previous slide and just made it nice, I guess. We'll use this also as a reference. We've put it in the top left corner. Now, of that list of variables that we're interested in, I've concentrated on 3 here: maximum height, time of flight, and horizontal range of the projectile. The reason that we'll concentrate on these 3, we're going to try to derive these 3 with respect to all the others. By doing that, we'll see the relationship between, for example, the initial velocity, the angle of launch, as well as the height. So we're going to see how they all relate to each other. Now, what we're going to be concentrating firstly is the horizontal range of the projectile. The reason that we're starting off with that is because, as we remember from before, the horizontal component of the projectile, ux, actually remains constant as you go along the path. So as this projectile is traveling along its parabolic path, that ux is actually going to remain constant all the way through. So you're going to get that same magnitude all the way through. This simplifies things. The reason that it's constant, remember, is because acceleration only acts as in a downward direction, only affecting this uy component. Uy goes down, 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 reaches here 0, and then it starts pointing in the opposite direction. For the horizontal component, it's all constant the whole way through. The good thing there is we can actually derive this range quite easily. If you look at this first equation here, s is equal to ut plus a half at squared. If a is equal to 0 in the x direction, in other words, there's no acceleration acting, then this term drops off and you're left with s is equal to ut. So let's write that up. So in the x direction, we have s, we have u, and we have a half at squared. So because ax is equal to 0, this will cancel off, and we're left with sx is equal to ux times t. Our t is just equal to that tf from before. So if we say our t is equal to tf and we're multiplying by ux, what we can actually determine is not just the distance, some distance away from the beginning point. We actually have r, right? The entire flight time multiplied by ux will give you the range. So that's almost an expression we can write down already, but let's expand out that ux as well. So let me just use this blue color on the side. So remember that ux is equal to u cos theta. The reason being that, as we remember from before, and just looking at this diagram here, we can actually express, not the best diagram, but we can actually express the relationship between u and ux as a right angle triangle. With this right angle triangle, cos theta is equal to the adjacent vector, which is ux, divided by the hypotenuse, which is u. So rearranging, we just get ux is equal to u cos theta. Therefore, we can write the range is equal to u cos theta multiplied by tf. So there we have it. We have a expression for the range given with respect to the other variables. The other variables here being the initial velocity, the theta term, in other words, the launch angle, as well as the time of flight. So now we've linked 3 of the variables to the range. Okay, so let's just put that result for the range under our diagram here. We're going to save it for later and come back to it. So now that we've done the horizontal range of the projectile, let's look at the next part, which is the maximum height. That's the HM that we've drawn here. And because we're no longer looking at the displacement of the x direction, in other words, now we're looking at displacement in the y direction, we are going to have to take into account the gravity. Now, remember, the gravity, in our scenario here anyway, is going to act in a downwards direction with a value of 9.8 meters per second per second. Now, one note to give here is that this is assuming we are on Earth, right? If there was a projectile motion question on the moon or on Mars or on some other planet, obviously this gravitational acceleration is going to be different. But let's just keep it simple and say we're on Earth, then this projectile here is going to experience that downwards 9.8 meters per second acceleration. And as it moves across, it's eventually going to reach this point. Now, what's special about this point here is that at maximum height, your velocity in the y direction is actually 0 because it's no longer moving upwards, right? It moves up, then it reaches maximum height and then starts going down. So if you imagine it going up to this point, what we can do is now concentrate only on that part of the flight from the initial point all the way to the maximum height. If we just concentrate ourselves on this point here, what we can say is, okay, let this be the origin of our coordinate system, and let us just concentrate on that y direction because that's all we're really interested in. And y is the initial velocity. At the maximum height, it's going to have a velocity of 0. So let's start writing that down before it gets a bit too complicated. So y direction is what we're interested in. We're saying the acceleration in the y direction is equal to negative g, right? It's 9.8 acting in the downward direction. We also know that the initial velocity, right, is equal to uy, right? V is equal to 0 because we know that when the projectile reaches its maximum point, the velocity there is going to be 0. So the reason we're writing all this down is because it's going to help us in order to figure out how to derive the maximum height. And S is what we're interested in. S is our question mark, right? We're trying to get to that S. So if we have S, V, U, and A, AY here, but you can just say A because we're concentrating in the Y direction anyway, we can see that this equation right here is basically the one we want to use because it involves V, U, A, and S, which is exactly what we have. So V squared is equal to U squared plus 2AS. So subbing everything in, 0 is equal to UY squared because we're dealing with gravity. It's going to be negative 2GS, right? So rearranging, if we're going to take this guy over to this side, we're going to say 2GS is equal to UY squared. S is equal to UY squared on 2G. Okay, now, even though we may think this is just the maximum height, and it would be if it wasn't for this right here. So the launch height does add to the maximum height, right? Basically what we've found is basically the distance from this point up to this point. We also need to add to that HL in order to make HM. So adding all of that together, HM is going to equal to HL, which is the initial height, plus UY squared on 2G. And what we've got now is the next part. Now, we should also recognize that UY can be expressed in a different form as well. So remember, UY is equal to U sine theta. Again, if I introduce the two components, UY, UX, we know that our U is there, right? So in this case, that's our theta here. Sine theta, because if we move this over to here, right, we can move around vectors, then the opposite angle is going to be UY, right? So sine theta is going to equal to UY divided by U. So rearranging UY is equal to U sine theta. So we covered this in the previous dot point, but just a refresher. So that means we can now plug that into here. HM is going to equal to HL plus U squared sine squared theta divided by 2g. Okie dokie, so just making that nice and neat, we now have our expression for the maximum height using the initial velocity, the theta angle, the launch angle, as well as g, basically the acceleration due to gravity, whether that be on Earth or elsewhere. You can replace that g with something else. And we also have our height with respect to where we launch it from. So because we've launched it from a ledge or a cliff here, we need to add that HL component. However, if this was 0, this would still apply. You just get rid of that and you have that as your maximum height expression. The last thing we're looking at here is time of flight. Because time of flight is dependent on sort of going up and then back down, we're also going to be looking at that y direction this time. But more importantly is we also need to consider 2 segments. Because this starts, as I was saying, starts off on a cliff or a ledge here, what we're going to be doing is considering how much time it takes for this projectile to get from its initial position to the maximum point, and how long it takes to get from the maximum point all the way down to its ending point. If this was a nice simple problem where the starting vertical level and ending vertical level are the same, in other words, they start and end at the same height, then you could just sort of figure out 1 and then multiply by 2. In this case, we have to split it up into 2 pieces. So let's start writing some of that down again before it gets too confusing. So y direction is the one of interest because we're sort of considering this up-down motion and we need to time that somehow, right? So that's where the t variables are going to come in from our equations on that right-hand side. Now the y direction, time of flight, we're splitting this up into 2 components. So time So the time from the initial position to HM, we're going to call T1, and T2 is going to be the time from HM back down to the ground. Okay, so we have that segment there as T1, from there to there will be T2, and TF is just going to be equal to the sum of T1 plus T2, so there should probably be an equal sign. So let's consider both those segments separately. Let's start with T1. What do we know about T1? T1 is the time taken to go from initial to HM, in other words, the maximum height. We know that initially that speed is equal to uy, right? And when it reaches that point, we know that the speed is equal to 0. We know that the acceleration is equal to negative g. In other words, we can draw that back up again because we're interested in that. It's acting in the downward direction. Gravity acts on all objects. So initial velocity uy, final velocity 0, acceleration is equal to negative g, and we're interested in time. So the equation, one of these equations with time in it is going to have to be used. So it's either going to be the first one or the second one. Now we also have s, right? We do know the height that the projectile reaches at that top point as well, right? But let's see if we can use an equation that only involves these ones. Well, if you look at these variables, we know that v is equal to u plus at is one that combines all of them, right? So if you plug everything in, 0 is equal to uy negative g t1. Rearranging this equation, so bringing negative gt1 on the other side, t1 is going to equal to uy divided by g. Now, as we stated before, we know that uy can be expressed as u sine theta on g. And there we have it. So we could have used that first expression there, s is equal to ut plus a half at squared. But because we know what v is, that second equation is a lot easier to deal with. We would need to solve a quadratic equation in order to use that first expression. So if we starting a new slide and keeping the t1 that we just derived, so t1 is equal to u sine theta g, we'll just keep it on the side here while we derive that secondary part. So remember that secondary part. So that was what we just derived, T1, and from this maximum point to the end, it's going to be T2, right? Now, again, remember, this is just a way of representing it. It's not actually in the x direction. We're talking about times t1 and t2. But let's just quickly rewrite the things we had before. Now we're considering from the maximum height down to the ground, right? So that ball is going to be traveling all the way down. Let's see what we know. U, the initial velocity, well, the initial y direction velocity, the initial vertical velocity is 0, right? That's what we used previously as v, but now that's our initial point, so u is equal to 0. A, as we've stated, is equal to negative g, it's acting in a downward direction. One other thing we know is s as well, right? The displacement. How far does it travel from here to here in the y direction? Well, it travels hm, right? However, because s is a displacement, it also has directionality. In other words, it's pointing downwards. It goes down hm distance, right? So we're going to have to be writing this as negative hm, not just hm. And so what do we have? We have u, we have a, we have s, and of course what we're interested in is t. We don't know what t is. We're going to call that t, t2. So what equation contains all those things? Well, this has s, this has a, and it also has u. And then the t that's left over, that will be used in order to express our expression. Right? So that's what we know. Let's write that out because that's what we're going to be using here. S is equal to ut plus a half at squared. Right off the bat, we can cancel out that ut because u is equal to 0. So s is now equal to a half at squared. Now let's sub in what we know. Negative hm is equal to negative a half gt squared, where t is t2. That's what we're going to name it. Now it's just a matter of rearranging, right? Let's first of all make both sides positive. So we're timesing both sides by negative 1. That's going to give you a half gt squared times everything by 2 divided by g. Now I'm just going to flip this around and now take the square root. And that's our expression for t2. Now, because hm has been derived before, we know that hm is equal to hl plus u squared sine squared theta on 2g. We can, if you want, plug that in to the equation. However, at the moment, I'm just going to leave it as it is and just say that tf is equal to t1 plus t2, which is equal to u sine theta on g plus the square root of 2hm on g. And that's our expression for the time of flight. Of course, we can write this in the expanded form as well. So tf is equal to u sine theta on g plus the square root of 2hl on g plus 2u squared sine squared theta on g squared, 2g squared. Those 2's will cancel, and that's what we'd be left with there. Now that's a bit more cumbersome, but effectively that's the equation that we're dealing with. What you can also see is that if hl is equal to 0, this term disappears, and you can easily take the square root of all these squares, and tf actually just becomes 2u sine theta on g. Okay, so now that's our 3 equations for the horizontal range, the maximum height, and the time of flight. So as we saw before, the range, the maximum range, is actually dependent on the time of flight as well. So if we really wanted to, we could actually plug these values into here as well. I won't do that here, but you are more than welcome to do that as well. There are a number of simplifications that occur as well that you could use, like trigonometric identities, to make the range a little bit easier, and depending on what the scenario is, it can be simplified even more. But at this point, we'll just leave it there. just because we've derived what we tried to derive, right? Without actually putting in any values. Like we did mention that gravity is negative 9.8, but we didn't plug that value in, right? Because we've left it as it is. What we've basically achieved is general derivation, right? Which is what the dot point was asking us to do. It was asking us to derive these the relationship between a number of variables, right? And we've shown that the range, the maximum height, and the time of flight, they're all interdependent, right? And depending on what the scenario is, whether it's this scenario, whether, for example, you're just starting on a level field and the projectile just goes up and then back down, right? So if it starts at the same level, then some simplifications can be made. For example, another scenario is, let's say it does start on a block, but instead of shooting it upwards, so yeah, instead of doing that, what we're saying that you can do is just shoot it horizontally, right? And then the projectile is sort of like half a parabola. These are some of the examples, and we're going to be actually going through those in the next video. In an exam, I can imagine that they may be able to ask you to derive one of these just based on these equations, right? It may not be one of these, but these steps that we've taken here are general enough to apply to any situation. So now that we have all of these, you can effectively sub things in, right? A lot of the times HL is equal to 0. So for example, this term here would be eliminated, right? However, what we'll do is we'll leave it there for now. If you have any questions based on that, please leave them in the comment section below. I can get to them. And if you have any other comments, including that you believe would improve these videos, I'm always looking to make the quality and what I sort of produce here at a better level. And I was thinking about any other avenues for spreading the good news of physics. If you have any suggestions on that, whether it's connecting through Twitch, for example, or YouTube Live, if there's things that you're interested in, please let me know, leave a comment, and yeah, maybe I can get that organized as well. Thanks for watching, and see you next time. Bye.